Good. And now share screen. All right. Can you all see my screen?
Yes.
Yes.
Perfect. So my idea for today is, as I wrote in the email, is to recall general stochastic integration for continuous semi-martingales and then talk about the exercise sheet 4. And the idea is basically I use here this nice program called Lux, where I can type and you immediately see what I'm doing. And after the session, you get the PDF file of the tutorial. Right. If you have questions, please just go ahead, because I have no feeling how fast or slow I am. And just, I mean, I really encourage you to keep doing the exercises because, well, they ensure, in this way you see if you still understand what's going on.
Hello?
You can, like, there's usually the deadline on Thursday. So what you can do, you can submit your solutions up to 1 week after the deadline. So I will always post the sample solutions. And if you think, oh, I have a different solution, which I don't understand if it's correct or not, then just send me still your solution and I will correct them. Because, well, the points are not super important, but what's important is that you check your understanding of the lecture. Are there questions so far from your side? You're still there, right?
Yeah.
Okay. Okay. So let's start with general semi-martingales because, as Felix pointed out, I mean, I was a bit sloppy at this point. So this is why I wanted to recall it and be more precise, in particular with the Lebesgue-Stieltjes integration. One final comment is, so I still have the free version. So after 40 minutes, I think there will be a break for 5 minutes and you will get a new invitation for the second session. So the idea is to do 2 sessions, each 40 minutes. All right. So let's come to semi-martingale integration. So what I haven't said precisely, so even in the case of general semi-martingales, the stochastic integration we are developing is called iter-integral. But anyway, so let's start. So as usual, we have a semi-martingale and we assume that it's continuous and the semi-martingale is called x. And by definition, it's given by a constant. So we start at the point x0 and then we have a local martingale. And we have a term which is a stochastic process, which is also non-anticipating, and it's a finite variation, right? And the goal for the past 6 lectures was basically to develop a stochastic integral of a certain class of integrants h against the semi-martingale x. This is what we wanted to develop. And what we did, our approach was to say, oh, wait, we have this decomposition. So in order to define this object here, we decided, well, we defined the integral with respect to local martingales and then the integral with respect to a process of finite variation, right? So that's, I hope I can write here now. So, well, it's not our, but approach, of course, fine, and now, well, we have this term here, which is the integration with respect to local martingales, and the second term was now I have even an autocorrect that's better than in lecture. And the second thing is this as classical integral, right? So that's the 2 things we wanted to do. And what I was somehow assuming, because you have a strong background in measure theory and probability theory, I was always just assuming that you know how to properly define this integral. And from now on in the financial part, we will always use this general integration theory. So I would like to recall today the construction or what's going on with this integral. And then come back to the Semi-Martingale stuff. So as I said, I mean, there is now, and the lecture notes are updated, and there's an appendix, I think it's A5, where there's now the integration, the Black-Stilches integration is recalled, and there are references given where you can check more details. Okay, so please interrupt me if I'm too fast, because I have the feeling I can be super fast. So this is what we want to define. I can copy paste, that's faster. So that's what we wanted to define. And I assume you have all seen Lebesgue integration, right? Any feedback from your side?
Yes.
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 That's good. So but anyway, let me recall it and then come back to the Lebesgue-Stilches integration. So what we have is we start with the function. We always assume that it's continuous. This is for simplicity for the course because we only consider continuous semi-martingale. So we assume we have some function a from the interval 0 to t to r, which is continuous, and let's start with non-decreasing. This means we can define or associate to this non-decreasing function finitely additive set function, right? So we consider basically the elementary set, so all the intervals, and we put 0 into it. So this is the collection. E is the collection of all finite unions of sets of these two forms. And then naturally you can define what the measure or the content of the such interval is, and it's just the set at 0, right? This is just AT, right? So this is how you start, and this is if you do Lebesgue-Stilches integration, the Lebesgue integration, the classical one. What you do is you consider here just the length of the interval, so this a is just t, right? And then there's the Cardori extension theorem, which is telling you if you have such a finitely additive set function, you can always extend it to a proper measure and in a unique way. So I can extend the mu star a to a unique measure on the Borel sigma algebra in a way that on these elementary sets, the additive function and the sets agree. And so this gives me a proper measure, and if I have a proper measure, I can start defining an integral. So if I come back to the setting here, I start with my continuous non-decreasing function, and I want to integrate a Borel measure, so Borel measurable function f. So f is, of course, from 0 to t, right? It has to be defined on the same domain to r. I do my standard procedure, namely I define it for simple functions f, right? Then I can extend it by a monotone class argument, for example, to bounded Borel measurable ones. And then I can extend it by probably a monotonicity argument to non-negative Borel functions. So this is what I guess you have seen. And if I then go the next step further, if I want to integrate now a general Borel measurable function, I do the usual trick. I decompose my function f into a positive and a negative part. So f plus and f minus are non-negative Borel measurable functions. And in this setting, I can then define my integral of f with respect to a, just as the integral of f plus with respect to the measure associated to a. So this measure mu a is the measure which was constructed via the Cardori extension theorem. And this is, then I subtract the negative part. And as long as at least one of these two integrals is finite, this is well defined, right? So but either the positive part or the negative part has to be really integrable, meaning having a finite value. Then I can, in the worst case, set it either to plus or minus infinity. So this maybe we should add here one of the two integrals is finite. Right. Because otherwise, I mean, if both are infinite, I could have here plus infinity, minus infinity, and then I need to think about what is the correct well, operation here. What does the minus mean? So let's keep it simple and say both integrals are finite, so this is well defined. Right? Okay, so but this is not yet enough to define this integral here. So the Riemann, the Lebesgue-Stieltjes integral we wanted to have, because we only know that this process A is of finite variation. So we need to extend this Lebesgue-Stieltjes integration a bit further. And now, like in a cooking show, I prepared some stuff here. So let's go here. So what we face in the course, if we want to integrate with respect to semi-martingales, that the function A is just a finite variation. So this means, maybe I should call it A here, and this is also not an X, that it's absolutely summable. So if I consider the increments of the over the interval 0 to t, which is the domain of the function A, and then I sum up, so take the supreme over all the absolute values of the increments, this has to be finite. So if this is the finite variation process, and we call the function A of finite variation, if this finite variation process takes finite values. Right? The nice thing about this function of finite variation is that we can always decompose it into the difference of two non-decreasing functions. Right? So if I have this is an if and only if relation, meaning if I have a function of finite variation, I can define, I can rewrite the function A as as an increasing part, which is my up arrow A. So this is the upwards movements, and then minus the downward movements. And this is, only possible if it's a finite variation. So if I have now such a function which is of finite variation, then I can again write my integral in the naive way as we expected. So if I have a Borel measurable function and a function of finite variation, I define my Lebesgue-Stieltjes integral just as the sum of, that's a minus, the difference of, well, the integral of f with respect to the upwards movements minus the integral of f with respect to a and the downwards movement of a. So meaning these are increasing functions, and I have already defined what this means. So the definition of this integral is just the classical Lebesgue integral. And all the properties, by taking always the difference of the sums, all the linearity properties you want to have from an integral, they are preserved by this operation. So this is the same idea as we go back here. It's what we do here, right? So we want that the integral is a bilinear operator, so meaning it's linear in h and linear in x. So as long as we take sums and differences, this is preserved. Right. So if we want now to define the Lebesgue-Stieltjes integral, that's the proper definition, and this is what we call the Lebesgue-Stieltjes integral. And what's often is also done is that the associated measure to h, a, which is a finite variation, is called Lebesgue-Stieltjes measure. So you need to be a bit careful, and this is what you might not have done yet in the, or never have done in the measure theory course, is that you have here signed measure, right? So this is a classical measure, so it takes positive values. This is a classical measure which takes positive or non-negative values, and signed only means that it's a measure which might take negative values. So there's no hard stuff going on. It's just a slight extension, and the key observation is actually this one here, that you can decompose any function of finite variation into two non-decreasing functions, and then you can use your classical integration theory due to Lebesgue. Right. Okay, so as I said, just, I mean, here are the lecture notes, and what you can find if you, as I promised you, here, if you go to A5, so this is in the lecture notes, you can find also some references. So there's the book of Yi. It's an English nice book. It's called Real Analysis, Measure Theory, and Integration Theory. And there's a German one, which is called, that's nice, Maßtheorie and Integrationstheorie, which is a classical book. I mean, they're very elementary, and this is basically what often is covered in the analysis 2 or 3 course. So this is just to recall you the general, the classical results. Okay. Okay. So far, you're still with me?
Yeah. Yes.
That's good. So I mean, please stop me, because I have no feeling how fast I am. Anyway, so let's understand a bit of the properties. And I mean, all the properties are basically all as you would expect. I think this is a general observation in measure and integration theory. If you set it up nicely, and this is how it's done now, everything works as you would expect, and so everything is nice. So the key message is everything works. So let's consider 2 Borel measurable functions and 2 function of finite variation, and we assume that the function f and h are integral with respect to a. So what is this? I mean, this is the integral with respect to the finite variation process, which is an increasing or non-decreasing function. So this is the classical Lebesgue integral. And what it's saying here, by taking the absolute values and the integral with respect to the finite variation process, is just saying that the positive and the negative parts are finite. So basically what we do here, we say that all these integrals are finite, right? Because I don't want to deal with the settings where we have to decide what's going on at infinity, right? Okay, so and now we have all the properties we want to have, namely the function t, so mapping the time to the integral process here. So consider the integral as a process in time. This is a continuous function. Here, let me. So why is this the case? So the argument is rather simple. It's just a dominated convergence theorem, right? So what you do is consider here the difference of s minus t. So that's nothing else than, what do you put in here? So you have to put here an indicator function. Let me make this, how do I rewrite it nicely? It's basically the indicator of so everything is gone which is less than 1. So you have this, and you have another indicator here, right? So right, so that's what you have. Let me give you here some brackets. Okay, that's nice. Okay, right, that's the same. And now, well, this object goes pointwise to 0. So that's to 0 as s minus t goes to 0.
Why the indicator functions? So one is from 0 to t and the other one is from 0 to s. And now you have, for some reason, factored out one indicator function.
Sorry. Okay, I should write these. So I mean, this is the difference. So so if I'm less than s, the integral, I mean, this side is 0. I mean, the integral here is 0, right? And now if I'm between s and t, this function is not 0 and this one is 0, right? Because the integral here is only going to s. So this is why I only consider the integral from s to t. I could also kill this indicator function and write it as this. This is better?
No, I just wondered why you had this the second indicator. I mean, if you have the indicator from s to t, why do you need the other indicator function? I mean,
if I kill this indicator function, what you see here is then, well, that's just 0. The issue is that this integral here is only going up to time s. So I extend this function here to time t.
Okay. So okay.
Afterwards.
This is an indication of extension. Okay,
yeah. Right. So I extend the function here, this f, up to time t by setting it to 0 after s.
Okay.
And then, I want to have a clean use of dominated conversion. So I don't want that the boundaries of the integrals are like depending on the s and t. So I put here the boundaries of the integral into the function f.
And the reason we keep the second part around is because the point s could have actually a positive weight.
Okay, this is actually the point where it's continuous cont, right? We have a continuous function here. So that's, if you have a atom at time s, then you don't have the continuity.
Yeah, but that's why you write it like this, to indicate that if it had positive weight, then you would have to deal with it somehow.
Yes. I mean, if it's, okay, I think the minimum you usually assume if you have some right continuity. So if A is only right continuous, also the integral is only right continuous. Right, because then you put the measure, the mass of a time t on the right side, right? And this is, so this goes to, and I mean, here this goes pointwise to 0, and then you have dominated conversion because this is all dominated by the function f. So this goes to 0 as whatever t minus s goes to 0. Right. All right. Okay. Then the property we use most, and I think this is what I think Felix asked me in his email, but I couldn't see the picture, by the way. There was just a red screen. Is that this function, again, mapping t to the barrier, the boundary of the integral, is of finite variation. Because this is important to keep the integral, I mean, the integral operation of a semi-martingale has to be a semi-martingale again. This is why we need this. And well, this is in the end actually not super hard if you just plug in the definition. So if we recall the definition, what we need to do first is we need to decompose the function f. So that's this function here into the positive and the negative part. And the second thing is, if we have a function of finite variation a, we also decompose it into the upwards movements and the downward movements. And then we plug in the definition. So this is in the end the definition of the Lebesgue-Stieltjes integral, right? So you have here you integrate the positive part with the upwards movement, then you subtract the negative part integrated with respect to the upwards movement, and then you have the positive part integrated with respect to the downwards movement, which is a minus, and then you have the negative part and the downwards movement, which is minus minus, so you have a plus again. So this is just spelling out the, where did I write it? So I take this as the first definition, then plug in this definition of the Lebesgue integral with respect to non-decreasing functions into the definition here of the Lebesgue-Stieltjes integral, which is the difference of the upwards and the downwards movements. And then you have here one's a minus and here minus. So this is how the plus and minuses appear in the equation below. Okay, where am I? Yeah, right. So now you rearrange these parts. So you take this one, stays here, and then you move the plus here. So the 2 with the plus you put together, and the 2 with the minus you put together. So this is here. And then you have the, I mean, these are increasing function because, well, everything here is positive, and this is also an increasing function, but with a minus. So you have here that this integral is nothing else than the difference of 2 non-decreasing functions. And since the verified variation is, I mean, in the end, just a norm, oh, I'm running out of time. Okay. Okay. So yeah. So this is, I mean, so you have a different of finite variation processes, meaning this is again of finite variation. And now, I mean, I will probably be gone in a few minutes. You have all the property you expect, right? This is what I somehow already started using in the lecture. So you have the associativity, you have the integration by parts formula, and you have the chain rule. And I mean, the later, I mean, these two are actually rather nice because if you consider the Ito formula, which you have done in the lecture, you can follow now these two rather fundamental properties directly by Ito's formula. Right? We basically proved the more general version of it. And now you can plug Ito's formula in to recover the integration by parts and the chain rule here. Okay, how do I see now?
I think the Zoom has a new, well, temporary features that allows you to have more than 40 minutes actually.
But I got a message, I mean, on my screen saying I have 40 minutes, and I should.
Yeah, but currently they have this Corona, I don't know, promotion that you can last more than 40 minutes. We can try it then.
Okay, we keep trying, and well, the moment I'm gone, you know what happens.
Okay.
Okay, screen again. Where is that screen?
I actually like the idea of 5 minutes break, but, so, yeah, but I don't know about the other.
I mean, if you like, we can do 5-minute breaks. Could you do a voting in the chat? Wait. Where is the chat? Do I see it? Are you writing the chat? Ah, there, I can see it. Break. Only one vote. No break, 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 break. You make sure that you're not double vote. 1, 2, 3, 4, 5, 6. 1, 2.
I think it's break.
I think it's break, yeah. Okay, you get a new invitation in 5 minutes. All right. See you.
Ciao.